Hi everyone, welcome to Mostly Math. Today, let's look at the cosmological equation. We have r as the scale distance. We have k, the curvature. It corresponds to 0 for a flat universe, or plus or minus 1 for a closed and an open universe. And we have the density rho. And we have some constants, which of course is the gravitational constant with some other crap. And this equation can be derived from GR, or general relativity, which we're not going to do today. Instead, we are going to let the rho be equal to lambda, the cosmological constant. And we are going to show that if we do this, we can separate variables quite easily to obtain an analytic solution. So let's go ahead and do that. Replace rho up here by lambda. And now we have the whole thing, 8 pi g lambda over 3 is just some constant, which we are going to redefine as h squared, which, yes, it turns out is ultimately related to the Hubble parameter, which is not going to be relevant in this video. It's just a constant. H squared is just a constant. And let's go ahead and separate some variables. If the k wasn't there, I'm pretty sure everyone could see what we would have to do next to separate the variables. But since it is, we can simply subtract it and see where it gets us. So now we have r dot squared is equal to h squared r squared minus k. And we know that r dot is simply dr by dt, of course. So we want to now take the square root of this, plus or minus the square root, of course, but we're just going to take the positive root. And yeah, r is dr by dt. And now it seems pretty clear that we can separate the variables. We have integral of dt being equal to integral of dr over square root of h squared r squared minus k, which we're going to rewrite as 1 over h integral with respect to r square root of r squared minus k over h squared. Yep, looks good. Next step in the separation of variables is to simply integrate both sides. Obviously, we can integrate dt pretty easily. So the equation that we're going to be solving here, may as well just put t right here. So we have this thing is equal to this thing. And now all we have to do is plug in the various values of k, and we will have our solution. So let's start with the flat universe. So that's going to tell us that k is equal to 0. And we have t is equal to 1 over h integral with respect to r over, well, this whole term goes away if k is 0, and the square root of r squared is equal to r if r is positive. Otherwise, it's equal to the absolute value of r. We can easily integrate this in terms of the log of r, of course. So we know that r of t is then some constant, r naught, times e to the ht, which should look familiar. This is the Hubble formula of the expanding universe, basically, for a flat universe. This equation is going to generalize that to the closed and the open universes momentarily. If we have a closed universe, then k is equal to 1, and t is equal to 1 over h integral with respect to r over square root of r squared minus 1 over h squared. I have written it in this fashion because we can recognize this integral as the, let's see, arc. I'm just going to write it. 1 over h. Now we have cosh inverse of hr. So the inverse hyperbolic cosine was what I was struggling with. We can now invert the equation so we can get r of t like we did above. So we have ht is equal to the inverse cosh of that. So we take the cosh of both sides and it becomes hr, and then you divide by h to get the final answer of this. R of t for the closed universe is equal to 1 over h cosh ht. Awesome. And let's look at the final case. Open universe, k equals -1, or t is equal to 1 over h. That was terrible. Integral with respect to r squared plus 1 over h squared, which is just a standard integral formula as well. You might guess it's going to be 1 over h sine h inverse sinh inverse hr. These are just horrible things to pronounce. Or we can invert the equation the same way. R of t is now equal to 1 over h sinh ht. And yep, that's pretty much what I wanted to show you in this video today. I thought it was a really cool illustration of how separation of variables can occur in situations where you don't think that it's likely, and how if you have a differential equation with a parameter in it, instead of solving the 3 equations separately, you can go as far as you can by keeping the parameter, in this case k, in the equation, and then plugging in the values of k later. I thought this was a pretty neat exercise, and if you enjoyed this, want to see more, subscribe. See you next time.